All right, good afternoon. I'm going to do my last lecture, which is on the three-body problem, which is also the name of a famous set of novels and now a Netflix series, which some of you have probably watched. This three-body problem is not nearly as complicated as that three-body problem. Also doesn't have as exciting a twist, although it does have a twist at the end, as you will see. All right, so yesterday we did a bit of the setup for this. What I've drawn here on the board so that I could get a running start, I guess, is the Feynman rules for the vertices and the dressed propagators that we've been working with over the last several days. So you have these already in your notes. I will say, for reasons, I think basically related to the notation I used when I first worked on this problem, I'm going to switch to small m's today. And although I can give you a reference where you see all this done in full glory with unequal masses, but it creates all sorts of nasty and not very illuminating factors related to mass ratios. So we're going to do this for distinguishable particles of equal mass. Okay. So the setup here is that we have two neutrons. Let's think about this as spin up and spin down, so they're distinguishable. I mean, you'll see, it's fine. And we have another particle, which is we call the core. Probably the simplest thing to do is to think about that as the proton. The proton and the neutron form a bound state. These two form a virtual bound state. And we want to compute the scattering of a neutron off the deuteron. So we define an amplitude for this, just as we define an amplitude for nucleon-nucleon scattering on the very first day. But this time, even though there are only short-range interactions between the nucleons themselves, there is a long-range interaction that can take place between the neutron and the deuteron. And that is the interaction that we played with yesterday, where the bound state emits a virtual particle. The extent to which that particle is virtual is dependent on the energy, actually, as we'll see, and it propagates across and forms a bound state on the other side. So this you can absolutely, it is a one particle exchange diagram. So I discussed with somebody yesterday, as you all were working on these, that although I drew these with like external legs, really they're amputated because they're amplitudes. So just something to be aware of as I'm drawing the pictures. I'll probably extend the legs a little bit, but make sure you remember in your head that they're amplitudes. They don't have propagators on the end. All right, so we drew some diagrams for this yesterday, and I pointed out, and hopefully you discovered by drawing diagrams as well, that there are two classes of graphs here. One in which the first interaction, well, actually, I'm sorry. There are three classes of graphs here. There's this one, and then as soon as you go, and then there are graphs which are sort of iterates of this one. Like this. And then there are other graphs in which this, the particle that's exchanged, the first exchange, let's call it, is a neutron exchange, not a core particle. And then this comes back. And so we end up in the state we want to end up in. So our mission here is to sum all graphs that start in the ND state and end in the ND state. But to do that, we're going to have to go virtually through what I'll call the CT state. Okay. Now, because the T state is not there's no bound state there, this is not a physical cut, although as we'll see, there is a three-body cut hiding in there. So in order to do this, the clue to how to write these equations is actually already here in these first two diagrams. You say to yourself, okay, well, after I get past this diagram, there are two possibilities. I could scatter this way, but then if I put my hand over this, what I'm left with is the same problem. What are all the possible scatterings between the neutron and the deuteron? It's the same problem that I started with. So we can resum all graphs in which the first interaction is the exchange of the core into this blob. Because after the first exchange happens, I'm back to exactly the same question. What are all possible scatterings between the neutron and the deuteron? Here, the situation is slightly different, but the principle is the same. After the neutron is exchanged, now I ask myself, now I have the situation that I want to know what are all the possible scatterings that take me from this CT scattering configuration to the ND scattering configuration. So as long as I'm willing to define an amplitude that represents the sum of all those graphs, so we'll call that a CT to ND, I can sum those, I can write that for that second class of diagrams. Then, of course, this doesn't give us a closed equation because now we have to figure out what this set of graphs is. So in the same spirit, we figure out the first thing that can happen, which is, we already know is this. I will probably not shade everything, right? But they're all dressed. So we draw the first thing that can happen, then we say, oh, okay, but after that first thing happens, in this case, there's only one first thing that can happen that can take us from CT to ND. After that first thing happens, now we are faced with, if we want to get to the ND state, then we have to sum all the graphs that take us from the ND state to the ND state. So this is the set of equations that gives us the amplitude for this process. This amplitude here exists sort of as an auxiliary quantity in this approach. You could actually substitute this equation in here and do without this amplitude, but it's a little more elegant when you're putting this on a computer to just write it as a set of coupled integral equations. I want to take a moment here to point out that what we've actually done here is resolve issues associated with the three-body problem in the same way that Fadayev did in the 60s. So I don't know if you ever thought about this, but if you want to solve the quantum mechanical scattering problem for three particles, you have a bit of an issue because you have to write down a boundary condition for the three-body wave function big psi. So in general, if you ask, I send in, say, a neutron and a deuteron, and I could have like the three particles all going out, it's not clear what boundary condition you should pick because they could go out in different configurations. They could go out when you go in the detector, you could have three free particles, you could have a neutron-deuteron configuration, or you could, if it doesn't really work here because it's not bound, but if the neutron-neutron state was bound, you could have the core off on its own and the neutron-neutron bound. So what Fadayev said was that in order to resolve this, you need to split this into different components depending on what the last interaction was. So what you do is you don't think about the whole three-body wave function, you think about pieces of the three-body wave function where the label on the three-body wave function is given by the last interaction before the detector. And the traditional way to label, so this denotes last interaction before detector. So if And the notation here is what the three-body folks call spectator notation. So that would correspond, so the N here is the spectator because the other two are interacting. And the C is the spectator. C is the spectator, we're here, because the two neutrons are interacting. So this is spectator notation. And this resolves the ambiguity in the boundary conditions for the three-body wave function, because in this piece of the wave function will sit the, if it exists, the two neutron bound state, and in this case of the outgoing state corresponding to this, and in this piece of the wave function will sit the outgoing state corresponding to that, where the brackets denote a bound state. So you can't write down a boundary condition for the global wave function because you don't know, because it has to contain all the information about the possible outgoing states, and you have different clusterings that can occur in the final state. But if you specify the last interaction before the detector, you know what the outgoing clustering was. And then you can write down basically it's just going to be an outgoing wave boundary condition on that piece of the wave function. It's a really clever and insightful thing to do to resolve this three-body issue. Yeah. So you're worried about last? Yeah, so you can still do it. This is actually what so there are four-dimensional versions of the Faraday equations which adopt the same structure. I think the interpretation is just a little bit different, right? Like it's basically you take the multiple scattering series and you pick the last T matrix, like because it's still going to look like G0. There's still going to be a last interaction in the diagram before things go to. I mean, let's discuss, maybe we can discuss afterwards. It's been a while since I've thought about that, but I understand that you're saying last is not well defined because of simultaneity. Yeah, right. But so I have to think about that because in a diagrammatic sense, last is still defined. Yeah. All right. Now here we sort of smuggled the Faraday of decomposition in because we're using these separable interactions. And so we were able to split the amplitude up into different final state and initial state possibilities. If we wanted to turn this into a three-body final state, we just have this thing break up at the end. But we're actually going to work at energies. For the purpose of today, we will work at energies such that the three-body breakup is not accessible to us. The 1 minus P12 here is an anti-symmetrizer because you have to anti-symmetrize if the neutrons are fermions. You have to anti-symmetrize between the neutron that's in the bound state and the one that isn't. It's a choice. So we're going to work at, I'll choose my zero of energy. I'll choose my zero of energy to be the place where all three nucleons have zero kinetic energy, right? And so I'm going to work at E less than 0. So scattering is still possible here because if I work in this regime, where B is the binding energy of the D thingy, then then this kind of scattering is still accessible, but I don't have enough energy to have 3 free particles. But the equations that I'm going to write down actually apply above E equals 0. It's just the analysis that I want to do is simpler if I consider just the case where only the two-body channel is open. Where by two-body channel, I mean this thing. And then if you want to go looking for three-body bound states, they live down here. And as I'll explain, you can get information on, you can get the wave function and the binding energy of the three-body bound states out of these equations too. All right. So I need to tell you about three-body kinematics. So everybody knows how to define total and relative momentum for two particles, but for three particles, well, for three particles, it turns out that you just do it in a sort of a hierarchy. So what we're going to do is we're going to take the momentum of this spectator neutron to be Q, and which means we're going to work in the overall center of mass frame of the three-body system. So that means that the momentum of this system is minus Q. So I'll say Pn1 equals Q, and then assuming equal masses, we then define a relative momentum between the neutron and the core, which is P. Three particles, two relative momenta. One of them is the relative momentum of the neutron or the spectator in general. These are the so-called Jacobi momenta. So you have to actually specify the spectator to define the coordinates. But if the neutron is the spectator, then Q is the momentum of the neutron. That means we're going to have to think about the two-body system in a moving frame, because the three-body system can't be stationary if the neutron is moving and this one isn't. So that's why, by the way, for once in my life, I kept the p squareds over 4m's there, because we have to think about the two-body system in a moving frame. But then once you figure out what its center of mass frame is, then the relative momentum for that pair is just the usual one. So in terms of these momenta, the overall kinetic energy of the three-body system is 3q squared over 4m plus p squared over m, for equal masses. And sometimes you'll see the notation that the usual reduced mass is m over 2, and then the reduced mass of the spectator relative to the pair is 2m over 3, which is why you get this funny 3/4 here. All right, so with all of that in mind, let's calculate. So what I'm going to do is just go over here and put some momenta on these lines. So this is Q. I'm going to call this Q prime. I'm going to call this minus Q prime. And I'm going to do the same. With great imagination, I'll call this minus Q double prime. But to make everybody who enjoys a good four-dimensional integral happy, I'm going to also introduce a Q0 and do the four-dimensional integral. So we'll put the Q0 down here, in which case up here we have to have E minus Q0 double prime. And then I haven't left myself a lot of room, but in this exchanged core line, if you apply conservation of energy, its energy is E, total energy minus the energy of this one, Q0 double prime, minus the energy of this leg here, because that's the energy available to this two-body system. And so when it splits up, the energy here is E minus Q0 double prime minus Q squared over 2m. And the momentum, sort of by a similar argument, is minus Q double prime. All right, everyone, I'm trying to do energy and momentum conservation. So you should check me. I'm going to focus on those first two diagrams, because once we have the kinematics for those first two down, the kinematics for the third one follows. All right, so let's just write down the loop like we were doing field theory, because actually we are. So IA ND to ND loop 1 maybe, if we're being really careful, is integral d4q double prime divided by 2 pi to the 4th minus I GD, because there's a coupling where the dimer breaks up. I divided by E minus, this is just a core propagator, so it's just a regular non-relativistic one particle propagator. Then the particle gets reabsorbed, so there's another minus I GD for that. Then we have I, and then we have the dressed dimer propagator. Now the energy flowing through the line is E minus Q0 double prime. The momentum in the line is Q double prime squared over 4m. Sorry, is Q double prime squared. So we have Q double prime squared over 4m minus ME plus MQ0 double prime minus I epsilon. And then last, but importantly, we have the amplitude again. All right. Now, we are going to calculate this thing over the next 10 minutes. By the time we're done, it's going to be a one-dimensional integral. Okay? So that's the goal. The goal is to reduce this to a one-dimensional integral. Why is one dimension good enough? Because if I get it down to a one-dimensional integral, I can use some quadrature rule. If you're really simple-minded, you could use like Simpson's rule. If you're more sophisticated, you could use like Gauss-Legendre quadrature. But I can use some quadrature rule to discretize the one-dimensional integral, and then I can turn this integral equation into a matrix equation. So if I can get it to a one-dimensional integral, I can pretty easily put it on a computer and solve it. All right, so let's sit here and look at this for a minute. Which integral, we have 4 choices, 4 dimensions. Which integral are we going to do first? Q0, right. So let's have a look in the Q0 plane at where the analytic structure is, because this will be instructive. So here we have a single particle pole associated with the particle that's going through at the bottom of the diagram. Is this pole in the upper half plane or the lower half plane? Lower, okay. And is it over here or over here? Yeah, it starts at 0 and goes this way as I increase Q double prime, right? Okay. And okay, let's do the same thing for, here is another pole. This one is a little bit more complicated to diagnose, but one thing we can see, I hope clearly, is which half plane it's in. Which half plane is it in? Sorry? This one. This is great, because now I'm going to like use colored chalk to match different propagators to different poles. Upper half plane, right. And so this one, because E is negative, and these 2 quantities are positive definite, you can guarantee that this one is actually, you know, sort of here, and then can only go down from there, where this point is E minus Q squared over 2m. And it also, that pole position actually also depends on the momentum argument that goes into the amplitude. So I didn't write that over here, but maybe I should have. All right. Next. So maybe, let's see, I'll ask a leading question. Is that the only analytic structure here? Yeah, there's a square root branch point. And so this occurs at Q0, the earliest this can occur is at Q0 double prime equals E. And the square root branch point is also in the upper half plane. So this actually occurs a little bit above, well, they agree when Q equals 0. So that sits here. And then there is analytic structure that is hidden from you because it actually comes in the following guise. So if I divide here by, suppose I divide top and bottom by GD squared, then this becomes M over 4 pi A. And so there is analytic structure in here as well due to the fact that if all of this is equal to 1 over A, I also get a pole. So that's actually, we'll come back to what that means in a minute, but this is also in the upper half plane. Okay, so that I should have used a different color chalk for, but okay. I did green for this one, right? All right, so for those of you who enjoy a good bit of analytic structure, the pinch between these two is going to generate the two-body cut. And if the energy is large enough, the pinch between this one and these generate the three-body cut. But the energy here, I deliberately chose E less than 0, so this one couldn't cross these two. Because the branch point occurs for Q0 double prime minus E is less than 0, which means Q0 double prime is less than E, and E is negative. But Q double prime is at what? Okay, so I mean, I can put that in too. But yeah, you'll see why I didn't. So that only makes it more negative. So typically when you're doing these analyses, you do them at Q double prime equals 0 because that's the worst it can be. It's not guaranteed, but normally the analytic structures just get further apart if you make Q double prime bigger. All right. Good. So which half plane do we want to close in? Lower, because the upper half plane is a mess, right? So yes. Now, when Dr. Kirscher is here next week, he's going to tell you about the four-body problem. And in the four-body problem, this is not as straightforward because you have diagrams in which you have basically overlapping cuts, at least if you're above the four-body threshold. All right, yeah, we can. Oh, okay, so now that we decided we can erase, we can close in the lower half plane, we can do. I'm going to erase that. So this means, I'm just going to use my notes for this. This is actually really great because all that means is we're going to stick in Q0 double prime equals Q prime, double prime squared over 2m, which, if you think about the physics of this, just means that that particle wants to live close. We're saying that the integral is dominated by points where that particle is close to its energy shell. So now this I, A, N, D to ND1 loop thing is equal to our integral D3 Q double prime over 2 pi cubed, minus I, I'm going to deal with the I's in a minute because they're just annoying, over E minus Q squared minus Q double prime. I'm going to square out the vector. And I'm going to multiply top and bottom by M. Yep. And so I substituted in for Q0 double prime, and then I squared out the vector and multiplied by 2m. And then I have, I divided by delta m over 4 pi a minus m over 4 pi times the square root of, so this becomes, oh, hang on, sorry. This should just have been Q double prime squared over 4. 3 Q double prime squared over 4 minus m e minus I epsilon. But the minus I epsilon is not going to matter for us because E is negative. And then I, A, N, N, Q double prime, Q prime. All right. So obviously now we can do some, I think I missed, I missed another one, sorry. We can, this times this is 1, this times this is 1, and this cancels this. So all the i's are gone. If the I offends you, pluck it out. All right, so now we do the next trick, which is to reduce this to one dimension. We're going to do that by observing that for low energy scattering, this will be dominated by S waves, and this amplitude will not depend on the angles. So at low energies, we can replace A, N, N, Q double prime, Q prime by A, N, N, Q double prime, Q prime. Now, just as I mentioned the other day, to make this precise, we should really do some spherical harmonic decomposition of this thing. We do like turn it into a partial wave amplitude with a YLM of Q hat double prime and a YLM star of Q hat prime. But the fact remains that when we did that, we would get like an integral equation for the S wave piece. And what I'm going to derive is the integral equation for the S wave piece, because it's the dominant piece at low energies. And it's the piece in which a bound state is most likely to occur. You think I should leave the L's? I should probably leave the L's, right? Well, yeah. Which, sorry, which? Oh, the A. Yeah, so that's a good question, right? So A actually does depend on the energy. I'm sort of smuggling that in because I'm thinking about this for particles in the final state that are on shell. So I'm having, it's going to turn out that I'm interested in this for, this is the on shell condition, because that's as we already, yeah, the total energy of this final state is going to be, oh, sorry, I made a mistake. That, because I have to consider the binding energy. The loop momentum? Yeah. Hey, loop energy. So because we picked up this pole, if we picked up this pole, we would have got a Q0 double prime that depended on E. But then our life would have been much more complicated because that's in the upper half plane. So this was I carefully chose the momentum routing so that the Q0 double prime would come out as simple as possible. If you choose a different parameterization of the loop, then your Q0 double prime might depend on the energy. As I said, the key point is that you're picking up the pole associated with this, right? And so you're effectively putting this particle on its energy shell. Ah, I see what you're saying. Yes, okay, good. That's an excellent point, right? So if we were working in a truly four-dimensional theory, the A could be a function of four momentum, not three momentum. And I snuck this in by just asserting that A was a function of the three momentum. Good. So if we did that, then we should worry about that if we have basically overlapping exchanges in time. But here we don't because of the structure of the pinball diagrams. So you don't lose anything by doing this. This is actually equivalent to saying that you can do the Q0 double prime integral in all the loops. So in any one of these loops, you can always, I erased the two loop diagram, but if you go through and look at all the loops you drew yesterday, you can always put the spectator on shell. So you can always reduce it to a set of three-dimensional integrals. That's not true if you have exchanges like this, right? Then you're right, then you're dropping terms as soon as you go from 4 dimensions to 3 dimensions. Yep, good question. Okay, but yeah, it's special to it's true, you can go to 3 dimensions either if the exchange is instantaneous or if all the exchanges are in the same time direction. So yeah, all right. Okay, so what quantity under the integral depends on the angle? So this thing here, right? So I'm going to just tell you that if you integrate this over the angle between Q and Q double prime, you get a log. right? You get, I always enjoy just saying this because it's fun, you get the 0th Legendre function of the second kind. So for those of you who like special functions, you know what that is. And if you don't know what it is, it's a log. All right, so when all's said and done, I'm going to leave the L's here. We get that ANN one loop is integral dq double prime q double prime squared over 2 pi squared m over 2q double prime log. I'm not doing all the algebra, which probably you will be grateful for. So the difference between this numerator and the denominator in the log is that you integrate from -1 to +1. So that's why you have a plus in the numerator and minus in the denominator. 4 pi over little m, 1 over minus gamma, plus the square root of 3 q double prime squared over 4 minus e times ANN. And it's a one-dimensional integral equation. So like I said, you could put that on a computer and you can solve it. So if I supplement this by the other pieces, actually the reason I focused on this piece is because this is the most interesting piece. This is where we get a really interesting phenomenon that I'm going to devote the last 15 minutes of my lecture to. But if for completeness, I will just say that the rest of the equation here is the structure is of the other piece is exactly the same. It's just that the dymo that's propagating in the intermediate state is different. But the exchange is the same. And here we have A, Cn, Q double prime Q. And then we have what the integral equation people would call the driving term. And that after you angle average that, you get another one of these Q0 thingies. So people who do Faddeev equations for a living have names for all these things. You know, this is like the kernel of the integral equation, kernel Kernel, not kernel Colonel. It's not in charge of the integral equation, but it's the thing that is sort of essential, the seed kernel in that sense. And this is called the driving terms. And of course, when you solve the integral equation iteratively, as you all found yesterday, you sort of get like driving term plus kernel times driving term plus kernel squared times driving term plus blah, 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 blah. So it's, in some operator sense, it's like a geometric series. And there's a whole theory of integral equations that rests on exploiting that. All right. So you can go and, you know, if we had a numerical component to this, and if we had more time, I'm not complaining, because like I got plenty of time to give my lectures. So this is not one of these, well, if my talk was longer, I could tell you all this interesting stuff, but they didn't give me enough time. They gave me plenty of time. I'm not complaining, right? But for reasons of time, and because it is essentially a numerical exercise, we could put this on a computer and solve it, but I'm going to tell you what happens when you do that. So the first thing you might want to ask yourself is, are you going to get into trouble with this kernel the way it is? So if you sit there and do a little bit more cancelling, you'll discover that the kernel, I'll call it K, because I'm not very imaginative, is 1 over pi Q double prime over Q, and there's this log. I'm just repeating what I already wrote, or I hope I'm repeating what I already wrote. And we have to think about two different regimes when we think about the properties of this kernel. So one regime is Q sort of small. Well, actually, there are three regimes, but the regimes that can get us into trouble are where Q double prime is big. But then because it's an integral equation, we're going to need to solve, in other words, we need in the end the amplitude for large off-shell momenta Q double prime because we need to close the integral equation. So we're going to need also to think about what happens when both Q and Q double prime are big. So in this regime, everything is fine. In this regime, this log thing, if you expand it out in this regime, or indeed if you just go back to the original 1 over blah, blah, blah squared stuff, you discover that that first term goes as 1 over Q double prime squared. All of this stuff. And then you have a 1 over Q double prime from the propagator at large Q double prime. And then the kernel is going to get multiplied by A. And maybe you can already see it from over here. At large Q, A is going to go like 1 over Q. So the kernel goes like 1 over Q double prime cubed. A goes like 1 over Q double prime. And the integral converges. If you don't believe me that A goes like 1 over Q double prime, you can actually define you can basically define an object where you rewrite A of Q as something else divided by Q and just substitute in and multiply through, and you're fine. So this regime is fine, but things are not quite so nice here. They're at least marginal. So there might, because in this regime, I can pick the log to be order 1. Right. Yeah, so, okay, good point, right? So here I really meant, I was hoping to slip that one under the rug, but in general, I'm going to look for energy, I'm going to assume that they're similar. Right, so I'm going to do scattering at momenta of order gamma. Right? Or I'm going to look for 3-body bound states whose typical momentum is the same as the typical momentum of the 2-body bound state. Okay. So the log, so if you take this whole object in this regime where they're both big, it goes like 1 over Q double prime. Did I flip that over? No, okay. And then this goes like 1 over Q double prime, and we have, I'm sorry, I got that the wrong way around. Let me start again. In this regime, we have a Q double prime over Q from out the front. The log is order 1. I have a 1 over Q double prime from this, and then I have a 1 over Q double prime from A. But this is a one-dimensional integral, and this is not enough to make sure things converge. So in fact, if you try to put this on a computer, you're going to have to put a cutoff on the integrals in order to make sure that things behave. Now, this is kind of an interesting result, and Dr. Kirscher will talk about this more next week, but this singularity here means that if you analyze like the spectrum of this kernel as an operator, it has like a large number of small eigenvalues. That's one way to think about what happens. But this is a little peculiar because if you analyze any of the diagrams in the perturbative series, they're all finite. But when you try to solve the integral equation, you have potential issues associated with the kernel. So I will summarize what happens when you do this analysis. This analysis is originally due to Russians called Skornyakov and Termatorosyan. I guess maybe not Russian, maybe Georgian, I'm not quite sure. Anyway, former Soviet Union people. So here, because Tuhin pointed out, I'll assume that I'm working at momenta that are large compared to the physical scales. I'm far off shell. But in this case, I need to know what happens far off shell because I want to close the equation. And in that regime, the equation looks like this. So then I can cancel this. Maybe I think I missed a factor because I got to include my 2 over root 3. So I can cancel this and cancel this. I can bring the 1 over q out the front, which I guess is the proof of what I said before. And I have that So now I'm going to pull the trick that I referred to briefly earlier. I'm going to multiply, I'm going to say that I'm going to think about what happens with this object, since I already told you that this thing is finite as q gets large. And this enables me to put another q double prime here. I'm basically just multiplying and dividing by q double prime under the integral. This is not necessary, but what it does is expose that now if you send q to, like, if you make a scale transformation on q, so you send q to c times q, and you change variables under the integral, nothing changes, right? Because if I change my units in which I measure momentum, this doesn't change. And here I have an invariant measure, dq double prime over q double prime. So this doesn't change. So this integral equation has continuous scale invariance. Everything in the integral equation, one way to think about this is the only thing that is the ratio of q double prime over q. So ANN q double prime is the solution of an equation with scale invariance. This is actually a direct consequence of the fact that we started with a theory that if the energy was set to 0 and the scattering length was set to infinity, had scale invariance, right? There are no scales left in this problem if we go to the ultraviolet, because we've forgotten about the energy and we've forgotten about the binding momentum. Those were the only physical scales in the problem. So what these former Soviet gentlemen showed was that if you try a solution that's a power law, because it's a scale invariant problem, then the number S is the solution of a transcendental equation. We proved this using the Mellon transform, which I worked out once many years ago and haven't done since. So this number, this is a transcendental number, is the solution of this equation. And that's the solution of the integral equation in the ultraviolet. This is a power law with the power given by the solution of this transcendental equation. Has to be a power law because it's scale invariant, and I'm sorry, I dropped my 2 over root 3 again. The particular transcendental equation you get depends on exactly what scale invariant kernel you have. Now, that's all interesting, but even more interesting is that in this particular, for the particular integral equation we have here, the solution of this transcendental equation is imaginary. So why is that interesting? Well, solutions to this equation come in pairs. If S is a solution, then minus S is also a solution. You can see that fairly quickly because sine is odd in S, this is odd in S, and cosine is even in S. So if S is real, this is not an issue because you don't want your solution growing as some power of S because then it won't be normalizable. But if S is imaginary, then both solutions are equally valid. So now I'm saying that I can have two solutions, Q to the IS naught and Q to the minus IS naught, and they're both valid solutions of this problem. And now we need some piece of information to choose the appropriate linear combination of these solutions. So the asymptotic solution for A and N looks like this. It has this logarithmic form because it's going to repeat, which means it's going to repeat when I multiply Q by e to the pi, is that right? Yeah, so if Q goes to e to the pi over S0Q, then the solution goes to itself. So this thing has like a discrete scaling symmetry. So the twist in the tail that I referred to is actually it's the tail of the wave function, at least the tail of the wave function in momentum space. And it's that you need some piece of information to fix the phase. So in effective field theory, if you need a piece of information that comes from the ultraviolet, that means you need a counter term. And the counter term that we missed is actually something that I think this gentleman asked me about yesterday. He asked me why we hadn't considered an operator that looks like, and I said to him, we're going to talk about, was this you? Yeah. No, okay, someone asked me about, oh, it was you. Okay, thank you. Sorry, I misattributed your insightful remark. So I said we're going to actually talk about this today. So yes, we can write down this operator. You might, how to put it, by naive dimensional analysis, this would be highly suppressed, but it turns out that as a consequence of the large scattering length, this is part of the leading order of the theory. So we add to the Feynman rules, this Feynman rule for the ND contact interaction, which the nucleon level would be a three-body force, which means we add another term to the integral equation. Don't worry, I'm not going to rederive the whole thing. It's actually very easy. It just looks like this. So we carefully designed this so that it only came in that one channel. And that is enough. And then you tune the strength of the three-body force to some piece of three-body data. You have a counter term, you're going to need a piece of data to fit it. So you fit the three-body force, for example, to the three-body binding energy. Three-body what, sorry? It's a contact force, yes. I don't know what genuine means in this context, Okay, so the strength of the three-body force in the integral equation is related to H. Does this really matter? It does. So to the coupling in the Lagrangian by this. And then you can show that as a function of the cutoff. This was shown in the original effective field theory paper on this subject by Badaki, Hammer, and Van Kolk, that H0 is going to run with the cutoff like this. And this is interesting because this is an example of a third kind of renormalization group flow, one that we don't normally see. So typically when we talk about the renormalization group flow, we talk about flowing to the trivial fixed point or flowing to the non-trivial fixed point. But apparently in Wilson's original, I haven't read it, so I probably should have, but I haven't. Wilson's original paper, he identifies three possibilities, which is that you could flow to a trivial fixed point or a non-trivial fixed point, or you could basically get stuck on some cycle and just keep flowing forever, so-called limit cycle. And that's exactly what's happened here. You have that the three-body force has gotten, it just keeps flowing on this trajectory like this forever. And these points here, where it goes through infinity and comes back at minus infinity, these are points where a new bound state appears. So what happens if you solve the problem numerically is that as you increase the cutoff, you get more and more bound states, basically because the interactions are giving you more and more attraction between the three particles. So up to this point, you have 0 bound states. Here you have 1 bound state. Here you have 2 bound states, and so on and so forth. But the three-body force just keeps on doing this forever and ever and ever. And what I didn't tell you is that this scale for the cutoff is logarithmic. So the three-body force has a log periodic running in this theory. And it never stops running. Some of you probably feel like that in your PhD or postdoc work, that you never stop running, but this three-body force also never stops running. All right, so I'm almost done. Let me tie this into a couple of things that I'm sure you'll hear more about next week. Yeah. It's not the experimental phase shift. It is just a phase. Maybe I should have called it phi. Because it's a phase that's associated with the solution in the far ultraviolet. Yeah, so you can, how would I say this? So if you don't include a three-body force, then when you put the problem on a computer and you solve, basically the details of how you implement your numerics will give you some value for this phase. And you'll get a random, let's say, three-body binding energy. Okay. So if you don't want that to happen, you have to put this constant h thing in. And then what that does is that by tuning that h, you're effectively fixing a particular value for this phase. And then you get a state, and then you can change the cutoff. But then you have to change h as you change the cutoff. And as you change h, as you change the cutoff, you can keep the three-body binding energy stable, but h lives on this limit cycle and has this log periodic running. All right. So all of this, the discrete scale invariance, the log periodic running of h, means that, oh, by the way, so this renormalization process has broken our continuous scale invariance down to a discrete scale invariance. So we started with a continuous scale invariance in the two-body problem. Then we started looking at what happened in the three-body problem. We found that the integral equation wasn't well behaved unless we did something. We introduced this three-body force, but then demanding a particular three-body binding energy, for example, breaks the continuous scale invariance. But there is still a discrete scale invariance. I already mentioned that the solution in the ultraviolet has this scale symmetry multiplying by either the pi over S0. You can also check by looking at my equation for lambda that the dynamics repeats if you scale the cutoff by e to the same number, e to the pi over S0. For this problem with 3 equal masses, this is 22.7. And so you have discrete scale invariance of the problem under multiplication by 22.7. So that means if you went to the infinite cutoff limit, you would actually have a tower of bounds, an infinite tower of bound states. There'd be the one you picked at B3, and then there'd be another one, which was 1 over 22.7 squared shallower, another one that was 1 over 22.7 squared shallower, and so on, all the way to 0. And there's infinitely many deeper states too, if you took the cutoff to infinity. And you can do this exercise and see it happen for yourself. Both of these are well-known quantum mechanical effects. This one was actually diagnosed in the 30s by Thomas, who pointed out that if you took a two-body zero-range interaction, you solved the three-body problem, the three-body system would collapse. It would have infinitely deep bound states. The fact that this goes on forever is the Thomas effect. And this geometric thing, and in particular this infinite set of states related by this geometric factor of 22.7 squared, is the Efimov effect. And I bet I can't square 22.7 in my head, but just so you don't have to, 22.7 squared is 515. So that means that is difficult to observe, but hang on a minute, I have one thing to say about that. But what happens in a practical problem is that these deeper states get regulated. Maybe you see one of these in your solution, but at some point, these get regulated because you don't believe the predictions of your effective field theory for states that are deeper than 1 over, let's say, the mass times the range squared. So there's some ultraviolet cutoff that's imposed on what you believe about your predictions that's imposed by the breakdown scale of your theory. And if you work with a finite two-body scattering length, that might provide some infrared scale that regulates this part of the spectrum, because it breaks the discrete scale invariance in the infrared. But if you can tune your system to live at unitarity, you can see at least one, maybe two of these states. And this was achieved in cesium gases in 2014 in an experiment in Innsbruck. It was a tour de force using Feshbach resonances to build three-body bound states at the unitary limit of cesium atoms cooled to very low temperatures. If you want to go and look at that, the paper is Physical Review Letters 112, 190, 401, 2014. And in fact, as Dr. Kirscher will explain, these three-body Efimov states are then actually associated with tetramers in the four-body system. So the same dynamics that generates these three-body bound states then actually guarantees that there will be two four-body bound states associated with each three-body bound state. But that's a whole other lecture. So this was supposed to be a lecture about nuclear physics. In fact, there's a nice paper by Rupak, Van Kolk, Eager, and I feel like there was another author, but I don't quite remember, but those three are certainly authors, arguing that there is an Efimov type state in the three nucleon system, but it's a virtual state, not a bound state. There's a claim that when we produce, which we will soon actually, the exotic nucleus calcium-62, that this could have an Efimov state. But Efimov states are hard to observe in nuclear physics because you need to have a three-body, sort of a primary three-body state that's deep enough that you can get a shallow state up here that's bound by a factor of 515 less without being disturbed by the two-body scales. And you need to be close enough to the unitary limit that you're not disturbed, that your two-body scale doesn't just completely mess up that shallower state. But what you can do in nuclear physics, and what I've actually done quite a bit of, is solve this set of equations and predict properties of the three-body system that maybe don't directly manifest the Efimov effect, but do manifest the effect that the three-body system is made up of 3 particles which are living near the unitary limit and so are associated with loosely bound systems. Okay, so effective field theory for nuclear physics is a valuable tool for describing systems with a separation of scales, and one scale separation occurs when systems are weakly bound compared to the range of the interaction. Then we can use it not only to organize the 2-body scattering, but to make predictions for electromagnetic properties, and we can raise it up to the 3-body system, where after we stabilize the system by introducing a counter term, we can make predictions for the properties of the 3-body and the 4-body system. All right, so with that, I want to thank you all for your attention. You all asked excellent questions, and I appreciated that you were very engaged with the material. I wish you best of luck with your graduate work or postdoctoral work, and I hope to see you again sometime in the future. Thank you very much.